Picture this. It's December 1941, Wake Island. Japanese forces are closing in on 450 Marines and 1,200 civilians. The Americans have no tanks, minimal artillery, and they're outnumbered 3-1. But they have 8 machines that will hold off an empire for 16 days straight. Not tanks, not artillery pieces, bulldozers. 8 Caterpillar bulldozers running the same diesel engine that would quietly become the most important power plant nobody talks about from World War II. Here's what nobody tells you about winning a mechanized war. It's not about having the fastest tanks or the biggest guns, it's about keeping them running. And while Germany was building complex V-12 engines that needed specialized mechanics, while Japan struggled with fuel shortages for their gasoline equipment, and while the Soviets were simplifying everything to the point of crudeness, America discovered something in the most unlikely place. The same diesel engine powering construction sites from Iowa to Illinois was about to become the secret weapon that kept the Allied war machine running 24 hours a day, 7 days a week, in conditions that killed everything else. The Caterpillar D-Series diesel wasn't designed for war, it was designed to move dirt. But that's exactly why it won battles from the Pacific Islands to the Western Front. To understand how a bulldozer engine became a war hero, we need to travel back to 1931, Peoria, Illinois. The height of the Great Depression, construction projects are dead, mining operations are shutting down, and Caterpillar Tractor Company is hemorrhaging money trying to sell massive crawler tractors nobody can afford to operate. Their gasoline engines are drinking 5 gallons per hour. Diesel technology exists, but it's German, it's complicated, and it's considered too finicky for American work sites. But Caterpillar's engineers, led by Art Rosen and Oscar Starr, see something others don't. Diesel engines have 40% better fuel economy. They produce maximum torque at low RPM, exactly where a bulldozer needs it. And most importantly, diesel fuel doesn't evaporate like gasoline, making it safer around hot exhaust pipes and easier to store for months without degradation. The problem? Every diesel engine in 1931 requires compressed air starting systems or gasoline pony motors. They're maintenance nightmares. So Caterpillar does something radical. They don't just adapt existing diesel technology, they redesign it from scratch specifically for the worst conditions on Earth. The result is the D13000 series, starting with the D4400 in their D4 tractor. 4 cylinders, 4.5 inches bore, 5.5 inches stroke, just 353 cubic inches. But here's where it gets interesting. While everyone else was chasing horsepower, Caterpillar obsessed over torque at 1,000 RPM. The D4400 made its peak 140 pound-feet at just 900 RPM. That's tractor-pulling, stump-ripping, mountain-climbing torque at idle speed. But the revolutionary part wasn't the power. It was the starting system. Caterpillar developed what they called the direct electric starting system. No compressed air, no pony motors. Just a massive 24-volt starter motor that could crank a diesel even at minus 20 degrees Fahrenheit. They achieved this through 3 innovations that sound simple but took years to perfect. First, a compression release system that opened the exhaust valves during cranking, reducing the starter load by 60%. Second, a fuel injection system that could atomize diesel fuel even when it was thick as molasses from cold. Third, and this is the clever part, a glow plug system that preheated not just the combustion chamber, but the intake manifold itself. Testing in Alaska during the winter of 1934 proved the system worked. A D4 with the new diesel started after sitting outside for 3 weeks at minus 35 degrees. It took 2 minutes of glow plug heating and 30 seconds of cranking, but it started. No other diesel in the world could do that. By 1935, Caterpillar had expanded the technology across their entire line. The D6 got the D6600 engine, 6 cylinders, 5 31 cubic inches, 180 pound-feet at 850 RPM. The D7 received the D7700, Same bore and stroke, but with 708 cubic inches producing 240 pound-feet. The D8, their largest crawler, got the massive D8800, 883 cubic inches, making 320 pound-feet of grunt at just 750 RPM. But here's what made these engines different from every other diesel on the market. Caterpillar designed them to be rebuilt in the field by mechanics who'd never seen a diesel before. Every major component could be accessed without removing the engine. The cylinder head came off with just 12 bolts. The fuel injection pump, usually the most complex component, was a simple single-plunger design that a farm mechanic could understand in 5 minutes. Even the pistons could be pulled through the top of the block without splitting the crankcase. The military implications weren't obvious until 1940. The U.S. Army Corps of Engineers was struggling with their construction equipment in Louisiana maneuvers. Their gasoline-powered bulldozers and graders were consuming 5,000 gallons of fuel per day per battalion. Fuel trucks couldn't keep up. Equipment was constantly stalling from vapor lock in the humid heat. Engines required overhauls every 200 hours. Then someone borrowed 6 Caterpillar D7s from a local construction company. The difference was immediate. The D7s consumed half the fuel. They ran all day in 100-degree heat without vapor lock because diesel fuel doesn't vaporize like gasoline. Most importantly, they just didn't break. After 2 weeks of continuous operation, clearing roads through swamps and pushing down trees, the D7s hadn't required anything beyond daily oil checks. Colonel William Heavey, watching a D7 push over a 40-inch oak tree, reportedly said, "That machine just won the next war." He had no idea how right he was. When America entered World War II in December 1941, the military faced a logistics nightmare. They needed to build airfields on coral atolls, clear jungles for supply roads, construct ports from nothing, and do it all while under fire. The equipment had to work in the Arctic cold of Alaska, the desert heat of North Africa, the humid jungles of Burma, and the coral dust of the Pacific that destroyed air filters in hours. The Army tried everything: International Harvester's TD-18 with its gasoline-start diesel engine, Allis-Chalmers HD-14 with its 2-cycle diesel, Letourneau's massive scrapers with their complex hydraulic systems. They all failed in different ways. The International couldn't start in cold weather without its gasoline system. The Allis-Chalmers required special 2-cycle oil nobody had. The Letourneau hydraulics leaked constantly in the heat. But the Caterpillar D-Series engines just worked. And here's the technical reason why. The D-Series used what Caterpillar called a pre-combustion chamber design. Instead of injecting fuel directly into the cylinder like most diesels, they injected into a small chamber in the cylinder head. This chamber, about the size of a golf ball, contained most of the compression heat. When fuel was injected, it partially burned in this chamber, then expanded into the main cylinder for complete combustion. This design had 3 massive advantages for military use. First, it made the engine incredibly tolerant of bad fuel. The pre-combustion chamber acted like a miniature refinery, breaking down heavy fuel molecules before they entered the main combustion space. D-Series engines ran on everything from submarine diesel to filtered crude oil. There are documented cases of D7s in the Philippines running on coconut oil mixed with gasoline when Japanese forces cut supply lines. Second, the pre-combustion chamber design reduced combustion shock. Direct injection diesels create a sharp pressure spike that hammers bearings and breaks crankshafts. The Caterpillar design spread combustion over more crankshaft degrees, reducing peak pressure by 30%. This meant the engines could use cheaper, softer bearing materials that could be cast in field workshops from melted-down brass shell casings when necessary. Third, and this is what really mattered in combat, the design was practically immune to dust and dirt. Direct injection diesels require injection pressures over 3,000 psi through tiny precision nozzles. 1 grain of sand destroys them. The Caterpillar system used just 1,200 psi through larger openings. Marines on Iwo Jima ran D7s for weeks in volcanic ash that turned oil into grinding paste. The engines just kept running. Let me put the durability in perspective. The standard military truck engine in 1943, the GMC 270, required a complete overhaul at 15,000 miles. A Sherman tank's Ford GAA VIA-8 needed rebuilding every 2,500 miles. The German Panther tank's Maybach VIA-12 lasted about 1,500 miles before catastrophic failure. D7's diesel engine? 10,000 hours between overhauls. That's 50,000 miles of bulldozer work, pushing full blade loads, not just driving down roads. The Army discovered D7s captured from abandoned Japanese positions on Guadalcanal, still running after 2 years of jungle abandonment. They'd been maintained by Japanese engineers who couldn't read the English service manuals, but figured out the maintenance by observation. The production numbers tell the real story. Caterpillar built 51,000 bulldozers during World War II. That's more than all the tanks America produced. Each one had a D-series diesel that could run for 3 months straight without shutdown. The D4 became the universal aircraft tug and artillery prime mover, able to pull a 150mm howitzer through Italian mud that stopped every truck. The D6 cleared million square yards of jungle for airfields, burning 1 gallon of diesel per hour versus 3 gallons for gasoline dozers. The D7 became a combat vehicle, fitted with armor plating and used to clear paths through minefields, bury enemy pillboxes, and even fight tank battles. There's a famous incident from Saipan where a Marine D7 operator named Aurelio Tassone took on 3 Japanese light tanks. The tank's 37mm guns couldn't penetrate the D7's blade. Tassone simply drove over them, the D7's diesel never missing a beat as it crushed 16 tons of enemy armor. But the real genius of the D-series wasn't combat, it was logistics. See, every gallon of fuel in the Pacific had to be shipped 3,000 miles from California. Gasoline required special handling. It evaporated in tropical heat, exploded when hit by enemy fire, and degraded after 3 months of storage. Diesel fuel was stable, safe, and efficient. A single Liberty ship could carry enough diesel to run 50 D7 bulldozers for 3 months. The same ship filled with gasoline would only power 20 gasoline dozers for 1 month. Do the math. That's 6 times the operational efficiency just from fuel logistics alone. The Germans knew this. Rommel's Africa Corp failed partly because their gasoline-powered equipment consumed 3 times the fuel of comparable diesel machines. They tried desperately to standardize on diesel, but their engines were too complex. The Maybach HL-230 in the Tiger tank had 800 precision parts in its fuel injection system alone. A D7's entire fuel system had 40 parts, and half were simple steel lines. The Japanese learned the hard way on Peleliu. They'd buried their defensive positions deep in coral rock, thinking American equipment couldn't dig them out. They hadn't counted on D7s with specialized coral rippers. The D7700 engine's massive low-end torque, 240 pound-feet at 850 RPM, could pull a ripper shank through solid coral at 2 feet per minute. Japanese commanders reported the sound of Caterpillar diesels working through the night, 24 hours a day, gradually destroying defensive positions they thought impregnable. But here's the technical detail that made night operations possible. The D-series engines had what Caterpillar called wet sleeve cylinders. The cylinder wasn't part of the block casting. It was a separate iron sleeve that dropped into a bore with cooling water around it. If a cylinder was damaged by enemy fire or wear, you could pull it out and drop in a new one in 30 minutes. No machine shop, no precision boring. Just unbolt the head, pull the piston, yank the sleeve, drop in a new one. The Seabees figured out you could preheat replacement sleeves over a fire, drop them in hot, and they'd shrink fit perfectly as they cooled. They rebuilt engines under combat conditions on Okinawa, swapping cylinders between artillery barrages. Try that with a German tank engine that required factory precision tools for any major repair. The standardization was brilliant. The D4, D6, and D7 all use the same basic piston design, just different quantities. Same valves, same injectors, same water pumps with different housings. A supply depot only needed to stock 20 different parts to maintain 3 completely different Bulldozer models. The Germans needed 200 different parts just for the fuel system of a single tank model. By 1944, the Allies had figured out something revolutionary. You could win battles with tanks, but you won wars with bulldozers. Every major offensive started with engineer battalions and their Caterpillar diesels. D4s pulling Bailey Bridge components, D6s cutting roads through the Ardennes forest, D7s filling in anti-tank ditches under fire, D8s carving airstrips from jungle floors. The numbers are staggering. In the Pacific Theater alone, Caterpillar bulldozers moved 2 billion cubic yards of earth. That's enough to build a wall around the entire equator, 100 feet high and 100 feet thick. They did it burning 200 million gallons of diesel fuel. The same work with gasoline equipment would have required 500 million gallons, assuming the engines survived, which they wouldn't have. The cold start capability proved decisive in the Battle of the Bulge. December 1944. Temperatures hit -20 Fahrenheit. German tanks, with their sophisticated gasoline engines, wouldn't start without extensive preheating. American Sherman tanks struggled with frozen batteries and congealed oil. But the D7 bulldozers attached to engineer units started every morning. 2 minutes of glow plugs, 30 seconds of cranking, and they were running. Those D7s cleared roads through the Ardennes forest faster than German engineers could block them. They pulled stuck tanks from frozen rivers. Most importantly, they kept supply routes open through the worst winter weather in 50 years. General Patton's famous relief of Bastogne was only possible because engineered D7s had cleared a path through supposedly impassable terrain. The maintenance statistics from the European theater are almost unbelievable. The average D7 in combat engineer service ran 22 hours per day for weeks at a time. Total engine failures requiring evacuation to rear areas? Less than 1%. The most common repair was replacing air filters clogged with dust, which took 5 minutes. Compare that to the Panther tank, where 60% were deadlined for maintenance at any given time. But here's my favorite statistic. The rebuilt engines were often better than new ones. See, the D-Series had what engineers call design tolerance stacking. Every manufacturing variation was in the direction of looser fit, not tighter. As the engines wore, they actually sealed better. The piston rings seated into the cylinder walls. The bearing clearances optimized for the oil viscosity. The valve seats work-hardened from repeated impacts. Marines on Okinawa reported capturing a Japanese D6 that had been stolen from Wake Island 3 years earlier. It had no maintenance records. The oil was like tar, the air filter was a wrapped cloth, but it still made full power. They changed the oil, cleaned the injectors, and used it for another 2 months of combat operations. The Soviet Union was so impressed they tried to copy the D8800 engine for their Stalinets 80 bulldozer. They got the basic dimensions right, but couldn't replicate the metallurgy. Their copies cracked cylinder heads after 100 hours. The secret was Caterpillar's proprietary cast iron alloy, with precisely controlled nickel content that provided flexibility under thermal stress. Too much nickel and the heads were soft. Too little and they were brittle. Caterpillar had spent 5 years perfecting the exact ratio. The post-war analysis is where things get really interesting. The Strategic Bombing Survey calculated that Caterpillar diesels saved the Allies 300 million gallons of fuel compared to gasoline alternatives. At 1940s shipping rates, that freed up 1,500 Liberty ship voyages for other cargo. That's 15 million tons of additional ammunition, food, and equipment that wouldn't have reached the front lines otherwise. Robert Moses, the master builder of New York, served as a consultant to the Army Corps of Engineers. He calculated that the Pacific Island Airfield construction program would have taken 12 years with 1930s gasoline equipment. With D-Series diesel bulldozers, it took 3 years. That's 9 years of war prevented by superior engine technology. The Japanese recognized this too late. Admiral Yamamoto's chief engineer, Captain Kameto Kuroshima, wrote in 1946 that Japan lost the war the moment America figured out how to mass-produce reliable diesel engines for construction equipment. We could match their warriors, he wrote, but not their bulldozers. Even more telling, when the Army evaluated captured German equipment after the war, they found the Wehrmacht had tried desperately to develop an equivalent to the D-7. The closest they got was the Hanomag K-55, which used a complex opposed piston diesel that required factory rebuilds every 500 hours. It had twice the horsepower of a D-7, but half the reliability. The Germans built 400. America built 15,000 D-7s. The real engineering triumph wasn't any single component. It was the system-level design philosophy. Every decision prioritized field serviceability over maximum performance. The fuel injection pump that could be timed with a screwdriver and a cigarette paper. The governor that used simple flyweights instead of complex hydraulics. The cooling system that worked with muddy river water when necessary. Modern diesel technology has moved far beyond the D-Series design. Common rail injection, electronic controls, emissions equipment that would baffle a 1940s engineer. But walk onto any major construction site today, and you'll still find Caterpillar diesels using the same basic architecture perfected for World War II. Wet sleeves. Pre-combustion chambers on some models, field-serviceable injection pumps. The Navy Seabees' motto is, "Can do." But their unofficial motto, painted on bulldozers from Guadalcanal to Iraq, tells the real story. In Cat we trust. Because when you absolutely positively need to move a mountain under fire, in freezing cold or blazing heat, with questionable fuel and minimal maintenance, nothing beats the descendant of those D-Series diesels that helped win World War II. Think about that the next time you see a bulldozer working on a highway project. That rumbling diesel engine carries DNA from machines that built the airfields for the Enola Gay, cleared the beaches after D-Day, and carved civilization from jungle wilderness while under enemy fire. It's the engine that won the war nobody talks about. Not through glamorous tank battles or fighter plane dogfights, but through the unglamorous, grinding work of logistics and construction that actually wins wars. The German Tiger tank was an engineering masterpiece. The Japanese Zero fighter was a marvel of efficiency. The Soviet T-34 revolutionized tank design. But the humble Caterpillar D-Series diesel? That's the engine that fed them all, fueled them all, and built the infrastructure that made their victories possible. Sometimes the most important engineering isn't the most complex. Sometimes it's the machine that just refuses to stop working, no matter what the world throws at it. What's the most underappreciated piece of engineering that changed history? Let me know in the comments below, and don't forget to subscribe for more stories about the machines that actually won wars.